Hello, thank you for watching this presentation. My name is Domingos Hadi. I'm from the Aeronautics Institute of Technology in São José dos Campos in Brazil. And I'm presenting the paper entitled Influence of Temperature Randomness on Vibration and Buckling of Slender Beams, which is co-authored by Everton Spoldaro and Luis Fabiano Dami, who are graduate students at the Aeronautics Institute of Technology. So the motivation of this study is that we all know that uncertainties can induce significant influences on the mechanical behavior of structural systems. And as a result, uncertainty quantification must be performed if we want to be sure that we are going to have a robust and reliable design. But an important point I'm raising here is that uncertainty can result not only from material and geometrical variations, which have been largely considered in the literature, but also from variability of the environmental conditions, such as temperature, humidity, and corrosiveness. We are particularly interested in the influence of temperature in this paper. And it is also known that thermally induced stresses can lead to modifications of the static and dynamic behavior of slender structures such as beams and plates and shells. And this effect is known as the stress-stiffening effect. What happens is that the majority of previous investigations on this influence assume deterministic temperature distributions over the structures. Of course, this assumption can be applied or applicable to certain cases, but it can be less justifiable in most of the practical situations in which the structures are subjected to complex combinations of heat transfer mechanisms such as conduction, convection, and radiation. In these cases, temperature cannot be controlled, and then it becomes appropriate to consider these temperature variations and the resulting thermal stresses as random quantities. So in this context, the present paper, we suggest a strategy for uncertainty quantification regarding the influence of random temperature fields on the modal characteristics, namely natural frequencies of a straight axially constrained beam modeled according to the Euler-Bernoulli theory. And in addition, since compressive thermal stresses can induce buckling, which is a kind of structural instability, the probability of failure accounting for this mechanism is also addressed here. So in terms of theory, we first examine here the internal forces which are induced by thermal effects. So we have show here a beam. Here I indicate the relevant properties: cross-section area, second moment of inertia, second moment of area, the Young modulus, mass density, and the coefficient of dilatation. And I also show here an arbitrary distribution of temperature along the x-axis. And we make here use two main hypotheses. First, the beam is thin, which implies that only temperature variations along the beam axis are relevant, and not, for example, the temperature variation across the thickness of the beam. And also we assume steady state conditions, which means that we are not accounting for variations of temperature in time. This also implies thermal equilibrium. In this equation here, we show the total strain of the beam, accounting for the thermal dilatation, this term here, and also the presence of these axial loads, which can be interpreted as the reaction forces exerted by the clamps here. And this function tau here represents the relative temperature distribution. I mean the difference between the applied temperature and the initial temperature field under which the beam is free of thermal stress. Coming back to this equation, as the beam is perfectly, assuming that it's perfectly clamped, we have the total strain equals 0, and imposing this condition here from this equation, you obtain an expression for the actual load, actual force induced by the constrained thermal dilatation. And this minus sign here indicates that dilatation implies a compressive force. Okay, so now the question is how to model the transverse vibrations of beams subjected to this thermally induced loads. Analytically, this differential equation here is the governing equation of motion for this problem. I highlight here the influence of the actual load in this term. And of course, for a given set of boundary conditions and initial condition, these equation of motion can be solved either numerically or analytically in certain cases. But in our study, we made the option for using a finite element approximation based on the energy approach. Some further information is given in the paper. Here I only summarize the main aspects. I show a typical element which comprises 2 nodes and 2 degrees of freedom per node, the transverse displacement and the cross-section rotation at each node. And all the discretization is made based on an interpolation here, where cubic polynomials are used as interpolation functions or shape functions. And after following all the standard procedure, formulation of kinetic energy, potential energy, and the use of Lagrange equations, we obtain this global form of the equations of motion, where I highlight here this matrix, which is named the geometric stiffness matrix, which again includes or takes into account the effect of the actual force. From these equations of motion in the time domain, we can derive 2 eigenvalue problems of interest here. This one is the one which provides the natural frequencies and the vibration mode shapes, and this one provides the values of the buckling loads and corresponding displacement shapes. Here we describe the case study we are interested in, consisting of a uniform beam subjected to random linearly varying temperature field. It's actually a clamped beam, as shown here. And the temperature field is parameterized in terms of 2 random variables, shown here, tau L and tau R, which correspond to the values of the temperature at the left and the right extremities of the beam. It can seem at the first glance to be quite arbitrary, this assumption, but in the paper we discuss some practical cases of interest for which this assumption would make sense. So since we have only two random variables, we can obtain this simple expression for the axial load in terms of them, and derive the expressions for the mean value and the variance of the axial load in terms of the corresponding quantities associated to each of the random variables. In this table here, we show the properties, both geometric and physical, of the beam used for the computations. Actually, these material properties refer to aluminum. And in addition, we assume that the temperature random variables follow uniform distributions with these limit values, and we assume that they are independent. So from basic structural mechanics, we can we have this expression for the buckling critical load, and having again this expression for the stochastic axial load, we can derive easily this buckling condition, okay, which means that the beam will buckle when the sum of the two random variables are greater than this limiting value here. We have also another interesting result, that since we have the z here represents the sum of the two random variables, so the PDF of z is given by the convolution integral of these two individual marginal PDFs of the random variables. And for the particular case in which the random variables follow uniform distributions, this is the shape of the PDF of the sum of these two variables computed according to this convolution integral. And then based on this, it's very easy and meaningful. By the way, there is a clear geometric interpretation here of how to compute the probability of buckling, which once computations are made, provide this value. The probability of buckling is 2.7%, derived analytically. And in parallel, we have performed Monte Carlo simulation based on 100,000 samples. And by counting the number of samples which lead to the buckling condition, we obtain an estimate of the buckling probability of 2.69, which is very close to the theoretical value I have just presented. And in this table here, we have also other statistical properties derived from Monte Carlo simulation of the actual load, the mean value, and the standard deviation, which was compared to the exact values, provide here very small errors. And the next numerical simulations, we evaluate deterministically the influence of the temperature on the first 6 natural frequencies of the beam, which is shown here. We can see the values of the natural frequencies against this parameter, which is the sum of the temperature at the extremities of the beam. What we can see immediately is that as this parameter, the temperature parameter, increases, the values of the natural frequencies decrease, and we can also see that except for the first natural frequency, in which this relation is nonlinear, we have a relationship which is linear between the natural frequencies and temperature for the other natural frequencies. And of special interest here is the fact that when one of the natural frequencies vanishes, which means takes the zero value as happens here, we have a buckling condition. So in this table we evaluate the sensitivity of the natural frequency with respect to temperature by showing here the values of these natural frequencies under two conditions. First, which is related to these values depicted on this line here, and these other values which correspond to the values corresponding to the crossings of these curves here, which the vertical line located at the value of 2022 here. Okay, so what is immediate to see is that we have a strong variations from one condition to another, and this variation is bigger for the low order modes and decreases for high order modes, but still these variations are significant for most of the natural frequencies in this case. So here we show, again, based on Monte Carlo simulations that have been performed, we show the PDFs for the 6 natural frequencies. And what we can see again is that except for the first one, the PDFs of the natural frequencies follow the same shape, as they have the same shape as the PDFs of the axial load. This is certainly due to the linear relation observed previously between the natural frequencies and the temperature parameters. The same, as you can see, doesn't happen for the first natural frequencies, certainly due to the nonlinear relation between the natural frequencies and axial loads. And these results are summarized in this table, which presents the mean values, the standard deviations, and the coefficients of variation, again showing that this variation, the dispersion is larger for the first natural frequencies. So based on this theory and numerical results, we can draw some conclusions, the most important of which is that temperature randomness indeed can induce significant variations of the buckling and eigenfrequency behavior of beams, and then this randomness must be taken into account in situations in which the temperature cannot be controlled. And in addition, modeling and analysis similar to the ones presented here for the simpler case of beams can be performed to other types of structural elements. And in the sense, we have been investigating the influence of thermal effects on the dynamic behavior of more complex structures such as metallic and composite plates. And of course, in these cases, temperature variations have to be modeled using two-dimensional random fields, and we have been discretizing these random fields by using Carnot-Loewe expansion. And for those of you who are interested in learning a bit more about these other works here, I mentioned one paper that has been accepted for publication in Mechanical Systems and Signal Processing, which must appear in the next weeks. Okay, so to conclude my acknowledgements of the authors to FAPESP, Brazilian Army, and Brazilian Research Council. Thank you for your attention.